All right, this is the practice problems from 19. This is what we should have done in class today, but I appreciate you letting me bow out given all the craziness that's happening for me at the moment. Hopefully we will all be back in good order in a few days. All right, so we are working on the practice problems 19 from section 5.1 and 5.2. We're being asked to classify all extrema, so that means find your local maxes and mins. You can use first or second derivative test here, your call. Either way, the first thing that we do is find our critical points, which is to take the first derivative and set it equal to 0. Subtract your 5, divide by 2, you end up with negative 5 halves. If you like the decimal, that's negative 2.5. And then we're testing that in either the first derivative test or the second derivative test. Now, the derivatives here are nice and easy, so I'm going to go ahead and take my second derivative, which turns out to be 2. And that is always positive, which means it's always concave up, which means that my negative 2.5 is a local min. So I have a local min at x equals negative 2.5, right? I didn't actually have to check anything because there was no x for my x value to be plugged into. The derivative is always just 2. Okay, number 2, let's try another one. First derivative here, again, same thing, we're finding critical points by taking the first derivative, so 6x squared plus 2x plus 8, and setting that equal to 0. I'm going to take a 2 out. Really, I can divide both sides by 2 here. And this will give me 3x squared plus x plus 4. Right? Remember that you can do it as long as you divide each term. And now I've got to factor that. So I'm going to use a box and circle, I think. Let's see if I can factor it. So 3x squared and 4 gives me 12. X, and I'm trying to get to a positive x. That's just not going to work, right? I need a negative somewhere to make that work. And so we're going quadratic formula instead. So this is equal to, x is equal to negative 1, which is your negative b. So your quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a, right? Where the a is the number in front of the x squared, the b is the number in front of the x, and the c is the number that's constant. Okay, so my b here is just 1, so I have negative 1 plus or minus the square root of 1 minus 4 times 3 times 4. So 4 times 4 is 16 times 3. 16 times 3, I believe, is 48 over 6. Now, that doesn't really matter because what happens here is I get negative number underneath the square root, which means that this is imaginary. So this is what we would say there are no real solutions. Okay. And that gives me no critical points. All right. And so if we have no critical points, we have no local maxes and mins. And that's possible. So we're done. So no local max or mins. Now let's confirm that. Let's go ahead and graph that. So 2x cubed plus x squared plus 8x. Let's go to my Wolfram alpha. And take a quick peek at the graph. So we're going to plot. And we said that was 3x squared, right? 2x cubed. Sorry, this takes forever. Plus x squared plus 8x. Go. And you can see that there are no local maxes and mins there. There does seem to be what could be an inflection point, but we're not looking for that here. So it makes sense that we don't get any zeros, right? No local maxes and local mins. Okay. Number 3. 5 over x minus 2. So remember that if we're going to take the derivative here, we're going to rewrite this as 5 and x minus 2 to the negative 1. Your other option is to use quotient rule. Don't forget that the derivative of 5 is 0, so it's going to wipe out a whole piece. When I go to take the first derivative then, I get negative 5 x minus 2 to the negative 2. And that's going to be negative 5 over x minus 2 squared. Now, for critical points, I'm setting both the numerator and the denominator equal to 0. So that's going to say, let's set the negative 5 equal to 0. There's no solutions to that. Doesn't make any sense. And the bottom, we also want to set equal to 0. That's going to give me x equals 2. Now, keep in mind that x equals 2 is not in the domain. And so if I were to try to do a second derivative test, first of all, I don't really want to because of the extra chain rule. But when you plug in the x equals 2, it's going to give you an undefined answer. So that means I'm going to think about this in terms of first derivative test. So my domain for this function is every value except 2. So we're going negative infinity to 2 and then 2 to infinity. So you can think about still breaking it there. That's fine. And this should appear here, right? So if there is a point where the function doesn't exist, that should pop up as a point where things are breaking in the graph. So a critical point is where there are breaks and changes in the graph, and so that should make sense for us. We're going to choose test points here, and so I'm going to go with 0 and 10. And I'm going to test in the first derivative. So if we plug in our 0 into the first derivative, you get something that is negative, so decreasing. And then when you look at plugging in 10 minus 2 is a positive number squared, and that's also negative because of the negative 5 up top, and you're still decreasing. So this is neither. What we do know is that this is going to be an asymptote, right? So this is at 2. There's an asymptote here. And so it's decreasing here, and then it's decreasing here. It's typically how that works. Okay, so it's possible that your answer is neither. All right, and lastly, number 4 and 5. So find all inflection points and intervals of increasing and decreasing. Okay, first derivative here, so y prime is going to be, and I'm going to reverse it, so I'm going to go right to left. Negative 2 times 3 gives me negative 6x squared plus 6x plus 36, and I'm setting that equal to 0. I'm going to divide through by negative 6, so that's going to be x squared minus x minus 6 equals 0. And I'm looking for two numbers that multiply to negative 6 but add to negative 1. I'm going negative 3, positive 2. Put in my x's. And that gives me two critical points, x equals 3 and x equals negative 2. Then we're going to go for the second derivative. So the second derivative, if we take the derivative of the first derivative, that's negative 12x plus 6. If we take negative 12x plus 6 and set it equal to 0 to find our possible inflection points, if I divide through by, let's see here, let's divide through by negative 12. That gives me negative 1/2 equals 0. And so that tells me that x is 1/2. You also could divide through by 6 and then solve it from there, whatever you'd like to do. That's my possible inflection point. So I am going to break up my domain, which is all real numbers, because this is a polynomial. I'm allowed to put any number I want in there. So I'm breaking it at negative 2, 1/2, and 3. So I go from negative infinity to negative 2, negative 2 to 1/2, 1/2 to 3, and 3 to infinity. Choose our test points. In the first interval, I'm going negative 10. Zeros in this one. I'm going to go with 1 and then positive 10. And we're plugging first into the first derivative. So the first derivative is this function here. Now what I'm going to do here to make my life easier is I'm going to factor out the negative 6. If I factor out the negative 6 and factor it, this is the same as this. And it's not equal to anything, it's just equal to my derivative. So I can actually plug into this one. Makes it a little bit easier. right? So if I plug in negative 10, don't forget the negative 6 is negative out front. So I'm going to have a negative times a negative times a negative. That's going to give me a negative, which means my original function is decreasing. When you plug in 0, you get something that is positive, so it's going to be increasing. Then you're plugging in 1. So negative 6 times negative 2 is positive, times positive 3 is positive. So still increasing. So 1/2 is not a local max or min. And then I'm plugging in 10. So negative 6 times 2 positive numbers give me something that's negative, so it's decreasing. That means I've got a local min here and a local max over here. Then we're going to test in the second derivative, so we can test for inflection points and concavity. So this time we're plugging in here, which I'm going to factor out the negative 6. So if I take out a negative 6, that is 2x minus 1. And I'm not going to set it equal to 0. There we go. So probably this one is actually easier to plug into. Your choice. When you plug in negative 10, that's a negative times a negative, which is positive, which means I am concave up. When you plug in 0, that's also positive, so concave up. When you plug in 1, you get negative times a positive, so that's a negative, concave down. And when you plug in 10, that's 20 minus 1 is positive, times negative 6 is negative, concave down. And you can see that my inflection point is here in the middle. So what we know is that there is a local max at x equals 3, a local min at x equals negative 2, an inflection point at x equals 1/2. It is increasing on those two middle intervals, so from negative 2 all the way up to 3. It is decreasing from negative infinity to negative 2, and from 3 to infinity. And then lastly, it is concave up on those first two intervals from negative infinity to 1/2. And it is concave down from 1/2 to infinity. Okay, so there is all my work for that one. That one takes up quite a bit of space. All right. Now, I am actually going to skip number 5 because this gets really annoying with calculating derivatives, right? The first one's not bad. I can show you that. Your first derivative here, it's going to be 3 times x squared minus 4 squared times 2x. So you actually get 6x times x squared minus 4 squared. So your critical points are not difficult. So this one gives you x equals 0. And this, if you factor it, is x minus 2 and x plus 2. So that gives you an x equals 2 and an x equals negative 2. So that gives me 3 critical points to work with. But then when I go to take the second derivative, this gets super annoying. So you got to go product roll. So it's going to be 6 times x squared minus 4 squared plus 12x times x squared minus 4 times 2x, which is a big old pain in my butt. So this is 6 times x squared minus 4. They have both all that in common. When you take that out, they have x squared minus 4. And I've got 4 plus 4x squared. So you end up with 6 times x squared minus 4. And you have 5x squared minus 4. This one's going to give you x equals plus or minus 2 when you solve it. This one's going to give you x equals plus or minus 2 over root 5, which is super not fun to work with. But we can work with that if we needed to. But I'm going to leave that go because it's just a little much for what we've got going on right now. Okay?